Okay, AP Cactus AB 6-1. This is like a little intro video, a little something different, and then we'll do kind of the typical thing. But I kind of want to show you guys some like real visual things to help wrap your head around this. Otherwise, I think it would be harder to understand. I think, they're already difficult. So this section is about this unit. We're going to be talking about related rates. And so I have some couple demonstrations to do for you guys. So while I'm doing this, I want you to try and think about things that are happening. So let me tilt this so you can see that all the way. So all right. So this vase, it's cylindrical, so it looks like a cylinder, right? So a lot of these problems are kind of 3D. Some are 2D, but so I'm going to be pouring water into this vase at a constant rate. Okay, so I'm going to try and keep it constant. I want you to think about the things that are changing in the vase. Okay, so pouring in at a constant rate. Let's say the volume in the vase is increasing, right? Volume of water. The height of the water is increasing. It looks like at a constant rate. Is the surface area at the top increasing? No, it's staying the same. The radius of the top is staying the same, but the height is changing, right? The height of this cylinder of water inside is increasing at a constant rate, and the volume is increasing. So, and let's see, we'll do another one. So this time I'm going to do vase. It's rectangular. And I want you to think about the same things. We're going to ignore this right now. And let's see what's changing. So I'm going to try and do it at a constant rate. So volume is changing at a constant rate. The height is changing. Is the surface area changing? Are the dimensions of the rectangle changing? No. So those are a couple simple examples. Let me pour this back in here. We're gonna do a couple more. We're gonna make them a little more interesting. Okay. But what's happening here is that there's all these different rates, and they're definitely tied together. The value of one affects the value of another. So, like the rate of change of the volume has something to do with the rate of change of the height. If you change the rate of change of volume, make it more, the height's going to increase faster, right? But they're not the same values. All right, next one. Make it more interesting. Rob, I think Hogan helped get these for me. So this one's kind of like, I want to think of it kind of like a cone. There's actually a lot of cone problems in this unit. I know the top doesn't really look like, but it's circular in nature, cross sections. And it slopes up. So same deal. I'm going to pour water in at a constant rate. And let's think about things that are changing here. So rate changes volume. The volume water is changing, positive, increasing at a constant rate. Oh, the surface area is changing. It's getting smaller. And then, whoa. At the end, did you notice the height was rising the whole time, right? But as it got more full and it got skinnier, the same amount of volume took up more space and the height increased even faster. So the last two examples, the rate change of the height was positive, but it was constant. Here, the rate change was increasing. The surface area was getting smaller. The area was getting smaller. The radius of the surface area was getting smaller, even as other things were increasing. So, and not only were the surface area and the radius decreasing, but they were doing it faster and faster as it filled up because it filled up even more. Okay, so I got one more base. We'll make it even, I feel like, even a little more interesting. We'll go with the sphere. Ignore the top. It's kind of like a sphere. And so, same idea. Let's think about things that are changing. Height, surface area, radius, volume. Okay. So volume's changing at a constant rate. The height's increasing, of course. Surface area is increasing. The radius is increasing. It's slower. And then we're passing this magic point. The height's still increasing. The radius and surface area are decreasing now. And then I don't know if you noticed at the end. So this has a lot of stuff going on. At first, the height was increasing, but it was actually getting slower and slower as the radius and surface area expanded. They were increasing, but again, slower and slower as it got more full and more wide. Once we hit this point, the height kept increasing, but it started increasing faster and faster and faster. The radius and surface area were decreasing faster and faster and faster as it became, smaller space for the same amount of water. So there's a lot of different rates that are involved. Now I got one more example, a little different. We'll do a balloon. All right. So we'll think of this as a sphere. All right. I'm going to try and let's pretend I'm increasing the volume of air inside at a constant rate, even though I'm not. But think about the things that are changing in the balloon. So the volume is changing at a constant rate, the volume of air. Now, I don't know, the radius of the sphere is changing. The surface area is changing. At first, the radius and the surface area were changing dramatically compared to what they were. But then as the balloon got full, the same amount of volume of air being put in resulted in not as big of a change in the radius. The radius was increasing all the time. But when there's more room in here for that same volume area to expand, it affects the radius less. And then the surface area was increasing less dramatically compared to what it was before too. So now we're going to go ahead and bring calculus into it. So that'll be a separate video. And we'll see how we can do some problems very similar to these and see how we can bring calculus into it.